Okay students, now we'll take up the portion which we have left out from the chapter solution. There are a few things, a very small portion of course it is left. One of the questions very frequently asked, if you are given a choice that to calculate the molar mass of solute by any of the colligative properties, which method would you go for and why? Okay, so here you can see the method is better. The method which is most appropriate to calculate molar mass of especially macromolecules is osmotic pressure method. The reason being, this method is better than the elevation of boiling point, that is delta Tb, and depression of freezing point method for the determination of the molecular masses of macromolecules. Delta Tb and delta Tf are not very widely used methods because the values of delta Tf and delta Tb come out to be extremely small. If you check out the numericals which we have done, you will find that the difference between delta Tb, that means difference in boiling point of the solution and the solvent, and that of freezing point also of the solution and the solvent, comes out to be very small, say around the range of 0.002, sometimes in the order 10 to the power minus 5 also. So we don't have such sophisticated instruments, no thermometer, which can read such small differences. So that is why it's practically very difficult to measure the differences in the temperature if we want to use these methods. Okay, so it's written which cannot be conveniently observed. Moreover, for biomolecules, the elevation of boiling method is unsuitable. As you know, most of the biomolecules they decompose at high temperature. So when you make them boil, the molecular structure doesn't remain the same. So whatever the molecular mass you will be getting by using that formula will not come out to be true. So, but you see, when you do osmotic pressure method, there is no delta pi. It is just pi. That means the osmotic pressure method, you need not calculate twice. You need not calculate the difference. Okay, and moreover, it is done at room temperature. So, considering all these factors, it has been found that osmotic pressure method is the best method to calculate the molar masses of especially macromolecules or biomolecules. Next week, I tell you to solve this numerical. This question has been asked quite a number of times in the board exam. Not very difficult sum, you can do it on your own. The portion which we left out is vent factor. So as you know that, if you remember when we were doing the numericals, every time we are taking the solute to be non-electrolyte. Okay, that means the solutes should not dissociate in solution. But there are enormous solutes around us which do dissociate or dissolve. When they dissolve in solution, they form ions. There are certain solutes which even undergo association. Okay, so what to do for such solutes? That means the the colligative properties become useless for them. So keeping all these in mind, a new factor has been introduced to calculate the molar masses for such solute also, and that factor is called vant factor, which is represented by the symbol small I. Now there are three formula used for calculating vant factor. You see, I is given as mc by mo. What does mc and mo stand for? Calculated molecular mass divided by observed molecular mass by colligative properties. So this is the expected value and this is the experimental value. Okay, if the molecules if the solutes ionize in solution, then the two values will not be same. So that's how you get one of the methods by which you get I. Another method is experimental colligative property. That means delta Tb, delta Tf, delta P by P naught, whatever. Okay, whatever the experimental colligative properties divided by calculated colligative properties. You note here, in the first case, when it is in terms of molar mass, here calculated molar mass by observed molar mass, but here it is calculated is here and observed is here. They are inversely proportional. If you check any of the colligative properties, the molar mass and the colligative property, say delta Tb suppose, they are always inversely proportional. So when it comes to colligative property and when it comes to molar mass, you see the two, they become inversely proportional to each other. then you see the third method, which is the most convenient and most widely used method, number of particles in solution after association or dissociation divided by number of particles in the solution before association or dissociation. So this is the most widely used formula. Say for example, if we want to calculate I for NaCl, what do? You know that NaCl dissociate to give you Na plus Cl minus. So number of particles after dissociation are how much? 1 and 1, 2. Before dissociation is 1. So I will be 2 divided by 1. So finally you get the value 2. You have to assume that the dissociation has occurred completely. That means 10% dissociation. Okay. Then you can see there is another solute given here, barium chloride. So we all know that barium chloride, if it dissociates in water, it will give you Ba2 plus 2Cl minus. So here how many particles we have after dissociation? 1 plus 2, that is 3. And before dissociation it is 1. So I value will be 3 plus 1, that is 3. Okay, so that is how we calculate the Van't Hoff factor I if the solutes are undergoing dissociation. But there are certain solutes which undergo association also. I hope we have some examples here. Okay, I don't find, probably have not given you. You see, if we have carboxylic acid, RCOOH, so it has been found that quite often two carboxylic acid molecules, they remain together in solution like this. Okay, they form hydrogen bond. So what happens? 2RCOOH becomes 1RCOOH twice. Sorry. So what happens here? So here if you apply the formula, what will be the formula for I? I will be number of particles after association, that is 1. Number of particles before association, that is 2. So it comes out to be 0.5 or half. So one thing you have to remember, those solutes which undergo association, for them I value is less than 1 for association. I value is more than 1 for dissociation, and I value is equal to 1 when the solute doesn't undergo any association or dissociation. So when we incorporate the value of I in all the colligative properties, we get this formula. You see, pi v become, earlier we know that pi v equal to nRT or CRT, and here we multiply by I to get the corrected value. Okay, that means for even electrolytes we can use it. Delta TB also, we knew this formula, delta TB is equal to KB WB by MB into WA. Here they are writing MA into 1000 if the masses are taken in grams, and then here we have to multiply by I. This way all the colligative properties, when we multiply by I, okay, we get the rectified value for rectified molar mass. So here they have given you example. You see, aluminium sulfate. Aluminium sulfate, we know when it will dissociate, it will give you 2 aluminium ion and 3 sulfate ion. So I value will be 5. Sodium bicarbonate, when it dissociates, it gives you sodium ion and bicarbonate ion. So there are 2 ions forming here from 1. So I value is becoming 2. They are ignoring the denominator. So this way the value of I can be calculated. Now comes a question. What is abnormal molar mass? You see here, molecular mass of NaCl when determined by colligative property doesn't come out to be 58.5, which is supposed to be the correct value, but it comes out to be 29.25, which is almost half of it. Similarly, the molar mass of barium chloride also comes out to be something different than expected. Then for benzoic acid also it comes out to be 244 instead of 122. So how we define abnormal molar mass? This question also comes in the exam, so you can please mark, this portion is marked, you take down this definition. If the molecular mass as determined by colligative property doesn't come out to be equal to the calculated or theoretical value, we call it abnormal molar mass. And what is the cause of abnormality? The cause of abnormality is either association or dissociation of solute in solution. Now here you find the relation. As you can see here, colligative property is directly proportional to number of particles. We know that. That's why colligative properties are also called democratic property, because they are very much dependent on number of particles. But if you check all the formulas just now, as we have seen, all the colligative properties, they are inversely proportional to molar masses. So ultimately, what is the relation between number of particles and a molar mass? Molar mass is inversely proportional to number of particles. So when number of particles increase, molar mass decreases, and that is what has happened in case of NaCl. You see, the correct value is 58.5, but it came out to be 29.25. And what happened in case of association? You see, the correct value for benzoic acid, just now we have seen the associated structure of benzoic acid, the correct value is 122, but it came out to be 244 because the number of particles decreased. So when number of particles decrease, molar mass increases. Okay, but the values whichever we have written, they are considered to be having 100% dissociation or association. But you know that organic substances, they do not undergo 100% association or dissociation. So for that we have to calculate alpha, which is called degree of dissociation. Alpha is degree of association or dissociation. That means to what extent the solute has undergone dissociation or association. So I'll give you the formula for alpha in terms of I, and based on that we'll be able to work out the numericals. I have given you some of the numericals marked here. You can see this is one, then one more here, then here this one you will be able to do. What is the value of I NaCl by considering the solutes undergoing 100% dissociation. Please try to solve this, and in the next class that formula for alpha with relation to I will be giving you. Thank you.